Other complexity classes, instead of defining complexity classes based on how much time it takes for a Turing machine to solve the corresponding decision problems, one could look at the space, that is, the number of cells the Turing machine will need. Definition 18.26. We say that the language L belongs to the complexity class P space if there exists a Turing machine T and a positive integer k and a constant c, so that T accepts x if and only if x in L and the number of cells T will use when given the input x is at most c times n to the k. In other words, T needs only big O of n to the k cells to decide if x is in L, where n is the size of the input x. As the Turing machine takes a unit of time to access each cell, the following proposition is immediate. Proposition 18.27. We have that P, which is a subset, or equals to P space. It is not known whether this inclusion is strict or not. The following containment relation is a little bit less obvious. Lemma 18.28, we have MP, which is a subset equals to P space. Prove that L is in MP. Note that as far as membership in P space is concerned, the running time of the machines is not important. Therefore, if T is the non-deterministic Turing machine that accepts L in polynomial time, we could modify T to get the machine T prime as follows. Let T prime be the deterministic Turing machine that carries out each computation resulting from a legal sequence of choices by T, but it does so consecutively in some specified order instead of concurrently, and so that each sequence overrides the previous one. Then this T prime is a deterministic machine. Indeed, in each stage, T prime takes a uniquely defined step since it takes the next step of the currently selected sequence. And the order in which the sequences are processed is determined. Furthermore, T prime uses polynomial space only, since each sequence, including the longest one, uses polynomial space only. Indeed, if a sequence S would take more than polynomial space to process, then T could not process that sequence in polynomial time. As it is not even known whether P space is actually larger than P, it is not surprising that it is not known whether P space is actually larger than MP. So far, every complexity class we considered contained P. How about the classes contained in P? In order to be able to introduce two interesting classes of that kind, we need the notion of logarithmic space. That is, we want to consider languages that can be accepted using big O of log n space only. Nonsense, you could say at this point, since n is the size of the input given to the Turing machine, so just taking the input needs n which is greater than big O of log n steps. Therefore, when considering these complexity classes, we will not count the part of the tape that contains the input as part of the needed space. We will only count the space needed for the actual computation. Now we are ready for the definition of two new complexity classes. Definition 18.29. We say that the language H is in L if there exists a positive integer k and a deterministic Turing machine T, so that for any input x of length, the size of x, the length of x, the machine T can decide whether x is in H using at most k times log of the size of x cells. A spectacular recent result in this regard is the following. Theorem 18.30. Let UST be the language of triples GST so that G is an undirected graph, and S and T are two of its vertices so that there is a path from S to T in G, then UST is in L. Theorem 18.30 was proved by Ulmer-Reingold in 2004. Definition 18.31. We say that the language H is in NL if there exists a positive integer k and a non-deterministic Turing machine T, so that for any input x of length x, the size of x, the length of x, the machine T can decide whether x is in H using at most k times log of the length of x cells. And a famous example of a decision problem that is in NL is reachability, that is, given input gxk, where g is a directed graph, x is a vertex of g, and k is a positive integer. A Turing machine must decide whether g has at least k vertices that are reachable from x by a directed path. The fact that this problem is in NL is the celebrated Immermann-Stielper-Paseany theorem. Note that if an algorithm can decide the reachability, then it can decide the UST, since we can set k equals to 1 and we can replace each edge of the undirected graph by two directed edges going in opposite directions. It is not known whether reachability is in L or not, but it is known that there exists a deterministic Turing machine that can solve reachability using big O of log n to the square cells. Note that unlike P or NP, the complexity class L does not allow for taking squares that way. It is clear from the definitions that L, which is a subset, equals to NL. Whether that inclusion is strict or it is not known. The following inclusion is a little bit more difficult to prove. Lemma 18.32. We have L, which is a subset, equals to P. The reader is asked to make an effort to prove this lemma on his own. The proof is provided in the solution of exercise 3. An enhanced version of the argument given in that solution proves that the inclusion in L, which is a subset, equals to P. Again, it is not known if this inclusion is strict. Finally, for a change, we mention one inclusion that is known to be strict. It is known that L is not equals to P space. The following chain of inequalities summarizes the weak containment relations we mentioned in this chapter. L, which is a subset, equals to, and L, which is a subset, equals to P, which is a subset, equals to NP, which is a subset, equals to P space. What is amazing about this chain of inclusions is that none of the inclusions is known to be strict. On the other hand, as we said, L is not equals to P space. Therefore, at least one of the inclusion in 18.1 is strict. So there is at least one strict inclusion between consecutive expressions to be proved in this chain. Is there just one? If not, which one will be proved first? Notes: a list of the 7 million prize problems can be found at the website of the Clay Institute. When this book goes to press in the year 2006, 6 years after the announcement of the $1 million offers for these problems, nobody has claimed 6 years after the announcement of the $1 million offers happen soon for one of the 7 problems. Nobody has claimed any of the prizes yet. Poincaré conjecture. A reader-friendly introduction to the topic of this chapter, just as to the topic of the previous chapter, is Herb Welf's book, Conjecture. Algorithms and a reader-friendly introduction to very enjoyable and fairly comprehensive graduate-level textbooks to the topic of computational complexity is Herb Welf's book, and the introduction to the theory of computation. Very enjoyable and fairly comprehensive